So, welcome, and while in the last two lectures you have been introduced to various aspects of what is this course about, and just a brief overview on visual computing from the classical way. So, now what we are going to do is, while you have learned down about the classical techniques of how to extract out features and then use those features in order to classify. So, the first part is basically getting down your first bits of the codes ready in order to extract out features. So, what we will do today is actually a lab session. It is a hands on mechanism, and I would go through down the process of how to set up your whole system PC on your own side, which you can use for doing these basic exercises. And since our codes are going to run down on Python, and that is the predominant modality on which we work, and for deep learning purposes we will be making use of PyTorch, which is a very specific deep learning library within Python. So, without much of a delay, let us get started. So, we have put down everything onto one GitHub page, which helps you get down one single consolidated window into all of your tutorials which will be conducted over here. So, if you look over here, so the address for this one is on GitHub. So, it is github.com/iitcliv/dlvc-nptel. Okay. So, it is just as mentioned over here. So, once you go down over here, the simplest stuff which you can anyways do is basically clone or download this one. To give you a basic reminder, please ensure that you are using a Linux based system in order to do that, because like we are going to make use of a very specific library called as PyTorch, which I will be showing you subsequently. So, PyTorch supports only on Linux based system. So, unfortunately you cannot do it on a Windows based system, though I mean you would be seeing that this desktop which is getting recorded on is a Windows based system, because we are connected down to another server system remotely in order to do all of this. So, I will not be complicating that part of the stuff, because most of you, I assume, will not be getting access to direct dedicated servers, and for none of the exercises which we are going to do in this learning based curriculum over here, you will not even be needing access to a full scale server to run down your codes. So, that does not necessitate, and you can pretty much run it down on your laptops as well. That there is no very specific requirement that your system needs to have access to a GPU, though it does help a lot for accelerating and doing it faster. Even a very bare one core i5 based CPU machine with barely about 8 gigs of RAM on board should be enough to do. Maybe a bit slow, but it will finish down within, say, much shorter than the lifetime. So, something which might be taking down a couple of seconds with a GPU system. So, in case of without a GPU on a CPU system, it might take down a few minutes, but you will still be able to see the results. So, this is the first foremost point, is to go on this GitHub page, and then this is where you do. So, we are going to populate it incrementally with all the lectures coming down one by one. As of now, today you would be seeing that just lecture 2, 3 and 5, which is placed over here. So, what we will be making use of is something called as Jupyter Notebook, and that is supported on Anaconda Python. So, the Python distribution which we make use of within these tutorials over here, and which you are also suggested to make use of, is the Anaconda Python distribution. Now, remember that there are two versions of it, Python 3.6 and Python 2.7. So, for much conformal support, we would be going down with Python 2.7, which, although to a lot of you might appear to be an older version, but major of these libraries for computer vision and visual computing tasks are what exist with Python 2.7 on legacy, and this is a time tested one. So, just first get down your Python 2.7, you can download it over here, and I mean, based on whether you are on Windows or you are on a Mac or Linux, and since most of you guys would be on Linux, so it's advised that you download the Linux version over here. So, you can click on these OSs over here, select your Linux, and then you get down your installer coming down over here. So, and then please check out whether you are using a 32-bit system or a 64-bit instruction set system. Most modern systems will be a 64-bit system. So, please download this 64-bit installer for x86 systems. And so, Power PCs are a different variant of processors as well, which are available just for few computers and generally for servers. So, most of you will not be having access to a Power PC. So, that does not need you to download this one. So, just ensure that you are on the correct version of Anaconda which you are downloading. Now, once that is downloaded and installed on your system, now The library which we will be using for our coding practices is what is called as PyTorch. It is quite simple, you need to just go on pytorch.org, and all of these links are actually given down on the GitHub page. So, if you are on the GitHub page, you see that there is a dependency list built up over here and there are links given down. So, this is for your Anaconda download, this is for your PyTorch download. So, once you click on that PyTorch, you will be ending up over here. Now, in order to get started, there are a few simple questions which you need to answer. So, one is what is your OS, you select down Linux. What is your package manager? So, that will be Conda, because we are going to use make use of Anaconda. Next is what is your Python? So, that is 2.7 for us, and what is your CUDA version? So, either you can choose 7.5 or 8 or even none. So, if you do not have a GPU over there, then just click on none, otherwise like for me it was 8. So, I am going to choose down 8 over here, and then you just need to run this command on your on your terminal for your Linux, and then that takes care of the rest of the installation. In case you get into some amount of problems over here, so you can always put it on the discussions forum on PyTorch, that can even be related to installations, and they would be the best guys to actually help you out rather than putting it back to us on our forum, because we were not always be equipped to solve out problems of third party software providers. Similarly, for Anaconda also, if you get down into any kind of a glitch, so you can just contact out these people, or you can just post it on the blog over there or on support. So, within the support team, they do make sure that they get back to you. Now, for CUDA, so the current version is CUDA 9, but you need to keep in mind one thing, that PyTorch is supported only till CUDA 8, and for that reason we will not be making use of CUDA 9, but we will be making use of CUDA 8 actually. So, with CUDA 8 it should be good enough to install PyTorch and get started. Now, given that once all of this is installed over there, so what you need to do on your terminal is invoke something called as a Jupyter notebook. Okay. So, Jupyter notebook is basically a web based UI for your coding environment. So, and then once you invoke your Jupyter notebook, you get this kind of a home screen coming now. So, based on whichever folder you are located in, so it is going to show you the directory listing within that folder. Now, what I can do is, once I have the directory listing, so I click on this particular one, so which is lecture 3, which I want to do. So, once I click, that invokes this particular page coming down over here, and this is what something I will be getting my initial access to. Now, if you look onto this page, there are some number of these bits and parts of Python codes. If you are quite used to Python coding, or if you are new to Python coding, then it still should not be much major of a problem, because I am going to explain you what each of these steps actually mean now. So, there would be these codes which go down, and that is exactly how we are going to solve the first part of it, and that is the first exercise which we are going to solve. So, you have already finished off classical methods of feature extraction, which included textures, and then majority of them were just texture based features. You had wavelets as well. So, we will be making use of those, and here is when I get you to show on them. So, what we are going to do is, let us do a very brief walkthrough of what is there. So, if you look on this, so let us just zoom like really big. Yeah. So, this should be a font size which is enough for you to understand. So, the first thing is that what I am doing is, you have this first line which is from Torch Vision import dataset. So, what it technically does is that as in any of your major codes, when major languages, you would be having a set of dependencies called as libraries. So, here also in Python you have your libraries, and these libraries, since it is an object oriented, so they are hierarchically packed within more containers as well. So, Torch Vision is basically a container within which there is another library container which is called as datasets, and the point is that I do not want to import complete Torch Vision over there. So, Torch Vision, this torch thing comes down from the library PyTorch, which we make use of, and there is a separate base for it which is called as Torch Vision, and this is just for the vision pipelines over there, the standard computer vision ways of doing it with Torch. Now, from there, the only thing which I would need for this particular exercise is dataset. So, instead of loading that complete library and eating up space on my RAM, I am just going to load down the datasets part over there. Then the next part is to include down is to import Python imaging library. This is just for reading and writing images and showing it out in a perfect way. Next is we will be making use of scikits actually, and this is the scikits image processing toolbox which we will be making use of. So, from there I would just need certain functions which are within the skimage.features. Okay. Now within that, the first thing which I would be making use of is get down local binary pattern. So this is a Python function, a .py file, which I need to import and have it ready for a lookup within my resources path. So I am just going to import this particular file. The next one is for gray level co-occurrence matrix. So that's a GLCM which we have already studied. And within gray level co-occurrence matrix, once you have that matrix coming out, you cannot make use of that complete matrix, because say you have a 8-bit image and you want to get down across all of these bits, you will get down some 256 cross 256 sized matrix. So instead of going through that one, we typically would like to compress that and get down certain uniquely describing features, and they are your gray GLCM properties, and that's what this particular function is going to provide you with. The other one is Gabor filter, and since Gabor filters are typically within a filters toolbox, so I would just be importing this Gabor function from the skimage.filters. More of what I do is I import this function called as pickle, and pickle is basically going to help me in storing my data. So this is a container. So if you are more of used to MATLAB, so you would be storing down your data structures, some sort of matrices or arrays which you have intermittently computed in terms of a .mat file. Here what we would be doing is in terms of a .pickle file, and for that reading writing part of it, I would need to import this particular library. Then I would also need access to my NumPy library, which is the numerical programming library for Python, and this will help me in defining my arrays, the data structure of arrays and everything. And in order to avoid writing down at every single point numpy dot some function call, I would just be providing a small acronym for that one, for numpy, and that is called as np. So every time I just write down np dot something, that will expand it in terms of numpy dot something. And also in order to plot down my figures, I would be making use of matplotlib.pyplot, and then that would help me in doing it out. Also I defined certain macros over here. So the first macro which I defined out, and that is more of to be consistent with Jupyter environment itself. If you are using some other environment, then you might not need to write down this first one, which is just if I am doing a plot, then let the plot be an inline plot, so that it appears on my HTML itself. So this is one part of the code block which let us get this one running. So the simple part is just go over there, and then you have run selected cell. So we just select that one and run it. So while it runs, you had seen down that small asterisk coming. So that's when all the codes within this block are running, and it has not yet completed. And once it's completed, this is the first time step of the run which has been done, and you get this one. Okay. So this is just a comment. So if you can choose to run it, but it doesn't actually do anything. Okay. So the next part over here, if you see, what I am doing is I am creating two data sets over here. So this data set is the CFAR 10 data set. So CFAR is basically a small images data set which is used for so there are 10 classes of items, images which are divided into 10 classes. They are small thumbnails of 32 cross 32 size, and you would be basically classifying them into these different kinds of classes over there. Now the point is, since we are dealing with visual computing, so we need to take in images itself, and these are all color RGB color images. So that's available directly within the Torch Vision data sets. So now we had imported Torch Vision data set over here. Now I can go into data sets, and then from there I import the CFAR 10 data set. Now the point is, when it imports locally, so it's either imported somewhere earlier, and then you can just fetch it and keep it within your folder called as CFAR 10. So this CFAR 10 is basically another folder which is created within my local directory. So you see your local directory over here, where within your Jupyter environment. So if you go down into this part, so you would see another folder called as CFAR 10. So this is what it needs to create. So initially when you are downloading this whole thing from GitHub, you don't see that directory anyways, because we did not upload the data set. That's a huge bulky file to be uploaded, and we just don't want to upload all of those because they are available from a secondary source as well to come down. So once first you download this whole thing, you will not be getting this folder called as CFAR 10. Now when you run this line, this is the first time when you will be getting down your CFAR 10. Now the reason I have this already running and this folder present is because I really want to make this faster. So if you have it already downloaded somewhere, you can put it within the folder called as CFAR 10, and that solves the purpose. Otherwise you need to download it from scratch. So here, like what it would do is it just goes over there and sees that files are already downloaded and they are perfectly. So, they will just be creating these two small data sets for me over there. So, I get down on CFAT 10 and within CFAT 10 I see these two. So, this part over here CFAT 10 python.tar.gz, this is my actual file which downloads over there from the source, and then within CFAT 10 batches it will be creating my training and test batches over here. Okay. So, now once that is done, so what I can do is I can move back onto my main directory over here and let us go to the next part of it. So, here what I am trying to do is get into the data set and try to find out what is the length of the data set, or how many number of training samples and how many number of testing samples are present over there. So, it is quite simple. So, it is basically find out, use the len function which gives you a length of array within the train data set and within the test data set. So, just run that part of it. So, these two pointers are already over there. So, we just find out what is the length over there, and then it just converts it to a string and prints it out over there. So, you know that your training data set is of 50,000 images and training and testing data set is of 10,000 images. Now, once that is done, the next part is we come down over here, which is feature extraction on a single image. So, initially what we will be doing is let's see what these images look like. So, what I am doing is I take down one of these images which is at the 0, 0 location. So, this is the first image present on my training data set, and then I store that as a variable img. Now, what I am doing is I convert this image to a grayscale map which is img underscore gray, and then I convert this into a numpy array. Okay. So, this whole thing which stays as a grayscale integer format. So, that will typically be coming down as some sort of a container with me. Now, that container I want to convert it to a numpy, and then let us just plot that one. So, if I run that, you would be seeing that this is sort of an image which you get down. Now, it is really fuzzy to understand, but this is basically if you like really go far off and then try to see into it. So, this is the image of a frog. So, the first data which we were looking down was just a frog. Now, once that part is done, next is we would like to compute out LBP features or local binary patterns for us. Now, for local binary patterns, what we are going to do is you would need the main image array. So, that is present over here as a numpy array, and this LBP is over here, they will be computing it in terms of a numpy array. So, you remember that we had already imported from skimage features this particular file called as local underscore binary underscore pattern for computing LBP. So, the arguments which go into this is the image array which is a grayscale one. Then this number over here is basically the number of points you would be taking around a central point. So, you remember clearly from our early discussions on in the last class on LBP, where you take one single point, and then if you are looking into its 3x3 neighborhood, you would be getting 8 such neighbors along that point which are at a distance separation of 1 pixel. Okay. And then what extra is added over here is what is the kind of a sampling you would do. Now, what it allows within these functions is that you can choose down any number of neighbors. You can choose 4, 5, 6, 7. Typically for a 3x3 that would not be a uniform pixel kind of a distribution, but you can interpolate and go down to those kind of forms. So, what we choose to do is we take a circular neighborhood with a uniform sampling over there, and that is what these arguments go down. You can get down further more details if you just search out on the help file for this function called as local underscore binary underscore pattern, and that would give you all the details over there. Next, the idea is basically once you get down these LBPs over there is to convert this LBP matrix onto a 8-bit format over there in order to get down what are the what is the range of these LBPs which come down. So, once you have this LBP converted over there, the next part is let's like see what this LBP feature on a point to point basis looks like. So, we compute this one, and this is more or less what is the LBP for that frog image which we get to see over here. It is really hard to actually find out whether there is a frog or something or not from so many points over there which are so distinctly spread. Now, from an LBP, what you can get down is you can compute out the histogram of LBPs, you can, which is a consolidated feature rather than feeding in this complete matrix of 32 cross 32 size. The next is you can get down, so once you have this histogram computed, you can get down the probability PDF over there for this from this histogram. Then that would help you to get down the energy and entropy as well. Now, once you have all of these, you can basically use energy and entropy as two different distinct one dimensional features in order to represent this, because the main purpose is that this whole image needs to be represented in terms of one single scalar value and a set of those multiple number of scalar values which will be your features which describe this image. So, for that what we do is we just evaluate this part over here, and I get down that LBP energy of this much and LBP entropy of this much is what defines all of this together present in this image. Okay. Now, once that goes down, the next part is to find it out on a co-occurrence matrix. Okay. So, in a co-occurrence matrix what I need to do is I need to get my image over there. Okay. The next point which you need to do is you need to find out how many, so basically at how many neighbors would you be looking. So, would you be taking down only one directional of it or two directional of it. The next argument over there is what is the orientation of your vector, whether it is at 0 degrees, 45 degree, 90 degree. So, based on whether it is east pointing it is 0 degree, if it is northeast pointing it is 45 degree, if it is north pointing then it is 90 degree, and so on and so forth. This number 256 is basically the number of gray levels you have in your gray level co-occurrence matrix to be computed, and this other parts on symmetric and normed are basically to show down how to handle down the boundary conditions present over there. Now, once you have done down this one, from your gray level co-occurrence matrix what is computed is another matrix of the size of 256 cross 256 which is present in this variable called as gray comat. Now, my point is that I cannot again make use of this 256 cross 256 matrix which corresponds to just a 32 cross 32 image, but I would try to get down more scalar values from that one. The first scalar value is basically to get down contrast, second scalar value is to get down dissimilarity, third is homogeneity, next is energy, next is correlation, and for all of these we make use of this separate function called as gray coprops, which takes in one of the arguments as a gray level co-occurrence matrix, and then whatever property you need to calculate it out. That is another scalar this. So, this is a small label descriptor which goes into the function so that it knows what to compute and give you. So, this will help me in getting, and these are the different measures for that one particular image. Now, from there the next one is to get into wavelets and do it. So, for we choose to do it with Gabor filters. Now, as you remember from your Gabor filter equations in the last class, so there would be two different things which you need to take care of within a Gabor filter, and that is like what is the frequency, and then what we are typically doing over here, that is that it will rotate and generate out. So, the first part is that you need to have your image given down over there, as well as what is your frequency at which you would like to operate. Now, the other part is what is the angle at which it is located and what are the variables over there. So, they are some things which are auto tuned within the system, or you can also choose to give down. So, you can read down within the details more over there. Now, given that at any point you will be getting down two components of your wavelet decomposition, one is the real value part, another is the imaginary valued part. Now, from there we just need to get down the magnitude valued part, and so we find out, we square and find out what is the magnitude. Now, once there, so you can just have a look into this part of it as well. So, you see that this is the real valued part of the Gabor filter output, this is the imaginary part, and this is basically the consolidated magnitude response over there. The next part is from your Gabor, you would we would like to get down some scalar representations rather than these kind of matrix representation, and they are basically your probability, energy, entropy, and then probability is used within this energy and entropy. So, you can calculate that and get down that the Gabor energy is this much and entropy is this much. Now, this is till now what we have done was just for one of these images, which was at the first location within my training data set. Now, in order to do it for training, I would need to do it for the whole data set, and that would mean that I cannot have any further looking into one image at a time. So, I need to run down some sort of a for loop within the length of my training data set, as in over here, in order to calculate this for the complete training data set, because I cannot do it on a one-to-one basis. So, what I need to do is define some sort of a matrix which is called as the training features matrix. So, this is a 2D matrix which is the number of rows in this matrix is equal to the length of the training data set, the number of columns is equal to the length of features. Now, how many features we found out was basically 2 plus 5 plus 2, and that makes it 9 features which we are going to have over here. Now, for this part what we do is we write down first for loop which basically ranges over the whole length of the training data set. Once you get over the whole length of the training data set, you need to find out one feature at a time. Now, once you have one feature at a time coming down, you need to calculate all of these features. One image at a time coming in, you will be needing to calculate all of these features. The first one is your LPP features, the next is your gray level co-occurrence matrix and Gabor filters. Now, once you have all of them, you need to concatenate that into one row matrix, and then you keep on concatenating one below the other, and you get your 2D matrix coming down. So, if we run this part, you see this verbose commenting coming down, and then it keeps on running. So, together that would finish it off. There might be certain bondings at positions, and you just need to escape it out. So, it would take quite some time because it needs to do it over 50,000 of those. But if you look through it, so it's pretty much fast, because there is this, like, the rate at which it's running down is not so tardy slow as well. In the duration of where we are speaking, you can already see this quite going on. So, we just have a verbose command given down over there. So, if you would like to get rid of this part, then the simple task is that you do not keep on printing this part over here, which is your print statement. So, if you do not print this part, then it's not going to show down how many of them are done and then you just need to wait till it's completely gone off. Now, once that part is done, the next part is basically to find it out on your test set as well. So, I just have to wait for some more time for this one to get over. So, let us just do a basic revision in that case. So, what I did was I have my predefined precursor coming down over here. Next, I take down my data set, and then I can decide to print on the type of the data set or not. But say if you are writing down a full-fledged code over there, you will not need to get these parts of the code running down. These were just for your explanatory purpose. So, you do not need to get down as to view one one image from your data set, then compute each of these features and then try to see them. So, these are parts which you can completely comment out, and then just start directly from extracting features from all images in your data set. Now, if you do not want to look into what is getting extracted, then you can just try to comment out this line or even delete this line. That's not much of an issue. So, this is just for printing out your status, and you see that this still keeps on running over here. So, let us see how far. Yeah, it should be quite close to finishing it off, because we are almost at 33,000. Try invoking another instance of. So, basically till then, when we have done, so the next part is that you just need to wait and observe till this part gets over for some more time. Now, once your features are extracted, the next part of your code is basically to go and look into what's the later part, which is about just saving out your features. So, I am just going to show it down onto this offline part, so that we do not just keep on waiting till that part gets. So, one is you have your training data set on which your features are extracted. The next part is to go down on your test data set and also extract out features and completely show it, and then eventually you can go and basically save down all of those features in terms of a pickle file as well, and then that is what goes down in the end part of yeah. So, now this is over, and the next part of it is basically to get down your testing once features extracted over the whole data set, and finally is where this part comes into play, and that is where you are normalizing out the features. The whole reason for normalizing out all the features is basically to get each feature dynamically varying within your train set in the range of 0 to 1. Now, what you need to keep in mind is that whatever is the normalization range you apply within your training set, the same thing has to be applied within your testing set, otherwise the nature of normalizations are going to quite vary. Now, once that is completely done, the next part is that you would like to save all of your feature vectors for being used in the subsequent stages. So, we just save down your training features and training labels as well as test features and test labels in terms of a pickle file, and then just print it out. So, once this part is complete, you need to get down extract features for your training one and for your testing set, then run the feature normalization and save it, and this should be good enough to get you started for the next lecture, which we will be covering down on classification with a very simple neural network. So, that thanks and stay tuned.